4. So I don't know. So for solid like steel, we have velocity is higher. So around 6,000 meter per second, and the density rho is 7.8, that is 7,800 kg per meter cube. And if we see the characteristic impedance, is equal to 4.7 into 10 to the power 7 kg per meter square per second. Whereas for oil and water, it would be of the first order. Say for water, it is C 1.5 into 10 cube meters per second. Rho is, of course, 10 cube kg per meter cube, 1000 kg per meter cube, and characteristic impedance RA. So this is RA is 0.15 into 10 to the power 7 kg per meter square per second. Now for air, this is C is lower because it is proportional to density. Rho is just 1.3 kg per meter cube. And more importantly, the specific acoustic impedance is just 430 kg per meter square per second. So therefore, there is a very large discontinuity when sound is traveling from air to water or air to steel. So lot of energy will be basically reflected back due to that discontinuity, so that we shall see the reflection, and reflection is very similar to the light reflection and refraction. Now, based on this property, based on this differential acoustic impedance, discontinuities, various discontinuities, and discontinuity or abnormalities can be estimated. For example, say water pipe there is some leakage, then also we can estimate that there is an interface of water to the air will directly come into picture without the intervening pipe in between. So if the sound propagates, there will be definitely a reflection from that point backward, or the intensity of the sound propagating forward will be attenuated due to the reflection discontinuity. Same thing can be postulated for medical ultrasound as well. So whenever there is some organ and impinging water or air medium is coming into picture, so there will be a good contrast that will be visually available to interpret the various organs, their placement, size, or any other abnormalities. Similar to acoustic impedance, we can also express acoustic intensity or power. W is product of effort and the response, that is P into U. So in terms of acoustic impedance, it is P square by RA, or in terms of flow, U square RA. So apart from this, when we interpret ultrasonic transmission, so attenuation is also an important aspect. This attenuation happens because of the various aspects of transmission of acoustic wave through the medium. It can be interpreted in terms of scattering and corresponding energy transfer. That is, certain energy it will not be transmitted but reflected back. But apart from that, there could be certain amount of energy which goes from acoustic domain to other domain. Other domain, mainly it could be, say, thermal domain, mainly to the thermal domain. So because of the mechanical vibration and associated friction, there could be heat loss. So therefore, certain amount of acoustic energy will be transferred from the acoustic domain to the thermal domain. So that will cause an attenuation or absorption of the acoustic energy. So there are attenuation of a plane wave. Attenuation of acoustic wave. Can be due to scattering, or energy transfer. from acoustic domain to the thermal domain. The treatment of energy transfer, that is acoustic energy transfer from acoustic domain to thermal domain, can be analyzed by detailed analysis of the thermodynamic behavior of the medium, so which of course we will not discuss, but this characterized simply by estimating the displacement field or the displacement amplitudes of the acoustic wave. So instead of discussing about the cause of this attenuation, we can simply take it as an attenuation factor and the attenuation coefficient. So this can be expressed in terms of changing displacement field d hat y is equal to d hat 0 exponential of minus alpha dy. So where alpha is the attenuation coefficient. So alpha d is the attenuation coefficient. Usually it is expressed per unit distance in meter inverse. So this is the amplitude attenuation coefficient. Similarly, the power attenuation coefficient can also be expressed in terms of W. Acoustic power or intensity acoustic power or intensity attenuation coefficient can be expressed as Wi is equal to W0 exponential of minus alpha W y. So similar to this alpha W is expressed in power attenuation and in meter inverse. So this is very similar to say light intensity or any other intensity like X-ray, etc. Everywhere same kind of expression is used. As I was telling earlier that this energy propagation through acoustic energy propagation through the medium can also be expressed in terms of scattering coefficient and absorption coefficient separately by defining certain forward scattering angle, backward scattering angle, etc. That we shall discuss if later, maybe after discussion of these plane waves. Now, the important another aspect that we have already discussed, that uh, reflection and refraction at a boundary of two material. So that is very important in ultrasonic instrumentation. Refractions at a boundary between two materials is important to characterize the inner structure of solid, liquid, or so it can be used. This also can be used to measure the thickness of the various material. So it is very similar to the plane wave reflection and reflection. Just what we generally treat for light. The same equations are for all plane wave approximations are similar, be it sound, light, or any other wave. So at a boundary, we have an incident wave and a reflected wave and a transmitted wave, and their angles are related. Incidence angle theta I, reflection angle theta R, which are same. Then we have transmission angle, and this incidence angle and transmission angle is related by Snell's law. So it is very similar to the reflection and refraction. So this is medium 1 is having C1 and R1, and medium 2 is characterized by C2 and R2. So reflection coefficient alpha R, energy reflection coefficient. There are two reflection coefficients that can be defined. One is amplitude reflection coefficient and another is energy reflection coefficient. So this is energy reflection coefficient, which is square of the amplitude reflection coefficient. And alpha t, the transmission coefficient. So this alpha can be derived for can be derived in terms of the incidence angles. However, if the angles becomes zero, theta equal to theta t, equal to 0 degree. So that means the ray is incidence perpendicularly along this perpendicular bisector. So in that case, the relation is simply in terms of the acoustic impedance. The amplitude reflection coefficient is R1 minus R2 by R1 plus R2, and the energy reflection coefficient is square of that. Whereas the transmission reflection coefficient is 4R1 R2 by R1 plus R2 square. The general expression, of course, can be derived by taking the components along this boundary. Along this boundary. So those components, the continuity of that need to be maintained. So by decomposing this acoustic wave component displacement field along the along this boundary and also perpendicular to this boundary, we can derive this relation. Maybe we can show it in some way. In general, if this is not 0 degree, then this would be for non-0 degree incidence. So that would be amplitude alpha would be in terms of theta I and theta I and theta R. Theta I and theta R are same, so the remaining terms will be like R1 cosine theta t minus R2 cosine theta I divided by R1 cosine theta t plus R2 cosine theta I. This is a simplified relation. After applying this relation to C1 sin theta t equal to C2 sin theta I, so in general this is coming from another relation in terms of sin theta I sin theta t. So that relation is can be derived directly from that continuity relation, and then this is simplified to this, and the transmission coefficient, the transmission part, that will be directly coming from the residual of the reflection part. So maybe later sometime we will have the derivation of this.
Hello, sir.
Yes.
Sir, R is the characteristic impedance.
R is the characteristic impedance.
Sir, then how is the intensity of light related to the characteristic impedance of the medium?
No, this is for the sound. I mean, it is similar to light. For the light, this will be refractive index N1, this will be N2, and this is N1, and this is N2. Okay.
Sir, in first we are defining alpha R is equal to this in terms of W, which is intensity of sound.
Yeah.
And sir, and then we are also defining it only in terms of R.
Huh? What is R?
Sir, R is the characteristic of the medium. Not the sound.
R is characteristics of the medium. Yes, yes.
Sir, but then we are relating it to the intensity of sound as well. But that factor we are not taking into account in this expression.
Yes, actually we can derive it. Okay. It can be derived. That's what I am telling, that we can make sinusoidal excitations, and then we can decompose those, like this one, just like optical one, this sound wave will have its equation like A1 sin omega t minus k into some distance z, where k is the propagation constant given by twice pi by lambda. Lambda is the wavelength. Okay. So in that form, then we have to assume that for this is medium 1, we have the frequency omega 1, medium 2 frequency of omega 2, medium 1 propagation constant k1, medium 2 k2. Then we shall show that omega 1 will be omega 2. Okay. And then afterwards we will equate those tangential component and the normal component, and then we can find these relations. I mean, that's a long relation, long derivation. So maybe sometime we'll do while discussion of that optical instrumentation. Okay. It
Okay,
is
sir.
similar, all plane waves are similar, be it sound wave or optical wave.
Okay.
Otherwise, it will take some time. Next day, we can derive it, or maybe today also we can do that, but it will take time. We may not be able to complete. So today, let us discuss just what are the other properties. Is it all right?
Yes, sir. Yes.
So in general, um, if we assume, if we neglect thermal conversions, then these two coefficients will be equal to 1. Okay. So because the reflected energy, sorry, and the transmitted energy sorry, will be equal to Wi. So if we divide it by Wi, Wr by Wi, Wt by Wi, that is equal to 1. So that is neglecting that thermal conversion. There is certain energy of loss to the thermal domain. So if we neglect that, then this will be established. So similar to the acoustic impedances, there are some characteristics, attenuation coefficients of solid, water and air. Some representative coefficients for solid, liquid and air are given below. Like for steel, attenuation, uh, this is very small, alpha R and alpha T. Water, so we are taking steel as the reference, okay, and then taking for water and then air. So these are the alpha R and alpha T values. So we can express the energy in terms or reflected energy in terms of transmitted energy in an exponential form. The ratio WR by WT, that is received power to transmitted power, so this one can be depends both on attenuation loss and the interface loss. Depends on both attenuation loss and interface loss. So together it can be written as WR by WT is equal to alpha T say 1 to 2 boundary, like here say alpha T maybe this is, suppose it is quartz to steel, as it is given, quartz to steel exponential of minus alpha W into the thickness T multiplied by alpha T S to Q. So therefore, during incidence, say from quartz to steel, there would be some boundary loss. Similarly, during emergence, steel to quartz, there will be also certain energy loss. In between, there will be an exponential factor of continuous loss, which will be going through the thickness as exponential of minus alpha W into T. So that way, the medium can be characterized by measuring the three losses together. This characterizes the efficiency of transmission through multiple medium. the interface losses can be minimized by putting some matching impedance medium matching acoustic impedance material in between. This is again, there are certain in between the two mediums of an appropriate thickness. So both these need to be maintained. The thickness of that matching material and also the impedance. The impedance would be the square root of the product of the two impedances, and the thickness would be proportional to lambda by 4, where lambda is the wavelength. So those things we shall discuss later. Here we will just discuss about the uh, matching impedance. So overall, transmission coefficient is maximized when R when intermediate acoustic impedance R is equal to square root of R1, R2. So this is again can be derived. So as I am telling that it will come in terms of wavelengths, and then the phase will be matched, because basically it is a plane wave. So we have to match the phases and the impedance functions properly, and then these relations can be found out. Again, maybe we can show it. This is same for uh, optical as well as electrical as well as acoustic. So suppose we have electrical waves propagating through two wires, then the characteristic impedance of electrical wave is given by square root of L by C, inductance by capacitance square root of that. And that is the characteristic impedance similar to the acoustic impedance. Okay, because the velocity is given by 1 by square root of LC. And here also it is similar. All plane waves have similar properties and interpretation. So there also we can see that we can have matching impedance at square root of Z1, Z2. in case of RF transmission. And here also for acoustics also we have that same relation. Acoustic impedance of the intermediate medium R, in which maximized transmission is R equal to square root of R1 R2. And for optical also that refractive index, that is anti-reflection coating, that is called in optics domain, that is called anti-reflection coating. And RF domain, that is the matching terminator, and acoustic domain, this is the matching layer. So n is equal to square root of n1 and n2, that is the anti-reflection coating refractive index. So therefore these relations are similar for all plane waves. However, these are important from making some for designing instruments, because suppose you have a hydrophone, so which is basically submerged in the water, then through that the signals are given, maybe in case of submarines transmission. So there we have to see that this kind of energy transfer from that hydrophone is maximized. So we have to have appropriate matching layers designed. Apart from this acoustic impedance, the thickness is also important. So with this, I think we will solve some small problems maybe next day. So anything else, any discussion question? Because we are simply discussing for the last few classes. Maybe we shall work out a few problems in the next classes.